In this first example, you have the population in a small town increases by 5% every 3 years. You're asked to answer these following questions and the round values to 2 decimal places. So what is the annual growth rate of the population? What is the doubling time of this population? And what is the actual doubling time of this population? The first one's asking if you use the rule of 70 to approximate it. So let's look at this. First, you need to come up with a formula that represents the situation. So here, a equals a sub 0 times 1.05 to the t over 3 power. A is going to be the amount after a certain period of time. A sub 0 is the initial amount, which you're really never given, and you really don't need it for this situation. You have 1.05 because you're increasing by 5%, so that would mean that you have 105%, or 1.05 as your common ratio here, or your common factor. And then you have t over 3, and the reason why it's over 3 because that 5% growth is every 3 years. And so this is the general formula that could be used for this situation. To get an annual growth rate, you need to make this formula 1 where you have this in terms of just t and not t over 3, because you want to get a percentage per year, because you need that for the rule of 70, and it's not bad to have it when you actually do an actual doubling time. So let's look at this. You're going to take this 1.05 t over 3 and be aware of the fact that it's the same thing as having 1.05 raised to the 1/3 power, all raised to the t power, because usually you would multiply these two exponents. That's how you get the t over 3. This 1.05 to the 1/3 is going to give you 1.016396,357 plus other decimal places that your calculator wouldn't show you. This is going to help you figure out what the annual growth rate is, because you're getting about 101.6396 or about 101.64% per year. And so if you round the percentage growth, you're going to have 1.64% per year. It's this value that you would use with the rule of 70, because you would get that the doubling time would be 70 divided by 1.64, which is about 42.6829, or 42.68 years. But that's an estimate. You actually have the ability now, with what was learned earlier in this chapter, to figure out what the actual doubling time is, to actually calculate it. Starting with this idea, and I'm using this version of the formula, because it's already been simplified a bit, but you want to keep all the decimal places, even if you have to store it into your calculator. You have a equals a sub 0 times 1.016396,357 to the t power. Well, when you're looking for a doubling time, you're looking for when this final amount is 2 times the original amount. Again, that's why you don't need to know what the actual beginning population is. You could also just make one up if you want, because what's going to happen is you're going to divide away that original amount from both sides, and this is going to cancel. So you'll be left with this 1.016 and change raised to the t power, and you're going to be left with 2 on the other side. Now here is where you're going to employ a logarithm. Again, it doesn't matter which logarithm you use. In this case, a common logarithm, log base 10, was used. And what that does on the left-hand side is allows you to multiply the t in front and just have the log of this number equaling the log of 2. And therefore, t is going to be the log of 2 over the log of 1.016 and change. And then you would work this out, and you get about 42.62 years. So not a big difference. I'm talking about number of years here, but it's still a difference. So that's the actual doubling time. That was the estimate. So it was a pretty good estimate. Looking at the situation here, and oftentimes with decaying, the rule of 70 and the actual half-life usually have a little bit more of a difference, because you're getting smaller each time, and as a result of getting smaller each time, you have smaller amounts to work with, and that can make a slight difference in how things are calculated seem much bigger. But you have a volatile substance is decaying at a rate of 14.2% every 10 hours. And we want to answer the same questions generally, except now it's a decay rate and half-life involved. It's decaying at a rate of 14.2% every 10 hours. So if you're losing 14.2%, you're keeping 85.8%. So that means when you use this formula, you're going to have A equaling an original amount A sub 0 times 0.858 to the t over 10 power, because it's every 10 hours that you're going to have this 85.8% remaining. Again, what you want to do is realize that in order to get your hourly decay rate for this situation, your unit rate basically, you have to take this 0.858 raised to the t over 10 power and realize it's the same thing as having 0.858 raised to the 1/10th power, all raised to the t power. And if you evaluate this, you get 0.9848015621, which means about every hour you actually have about 98.5% remaining instead of the 85.8% every 10 hours. So your decay rate is going to be the fact that, well, this is going to be 98.48% remaining after each hour, which means you're going to be losing 1.52% every hour. And it was this value here, ignoring the negative, where you would use the rule of 70 to calculate the half-life. 70 divided by 1.52 is about 46.0526, or about 46.05 hours. And that's the estimate using the rule of 70. To calculate the actual half-life, going to start with this formula here. And again, a half-life means that this amount here at the end of this time period is going to be half the original amount. And so when I divide both sides by that original amount, I get 0.9848, so forth and so on, to the t power equaling 1/2. I would then use a logarithm to figure out what's going on here, because putting the logarithm here lets you move this t in front and make it a multiplication. And so I have the logarithm of that large base equaling the log of 1/2, which means that the time would be the log of 1/2 over the log of 0.9848, so forth and so on. And then you would get about 45.259, or about 45.26 hours. So a little bit more of a noticeable difference between the estimated value and the half-life, but you'll tend to see that more frequently with half-lives because of the fact you're decaying and the amount that you're working with is decreasing. But that is the end of this problem, and that is the end of this video. If you have any additional questions, please make sure to bring them up during our class session.